All right, here we go. Newly calibrated board. All right, so today we're going to kind of finish up our unit on the basics of work and energy, and we're going to be focused on some calculus-y stuff. All right, we're going to focus on how to use calculus to deal with work and energy, and specifically how to deal with some of the graphs that you're going to deal with when you're dealing with work. All right, so here we go. All right, so one of the things that we've learned at this point is that if you've got a force along some axis and displacement along that same axis, that you can calculate the work done by that force by multiplying the magnitude of the force along that axis times the displacement along that axis, right? Yes, but that is only true if the force is constant, right? Remember, this equation here is only valid if the force is constant. All right, so for example, in the case of gravity, force of gravity is a constant force, right? It's equal to mass times g, and then the negative indicates the fact that it's down. All right, and so if you wanted to calculate the work done by gravity, you would multiply the force of gravity by the displacement vertically, right? Okay, so one of the things that we might want to do is we might want to make a graph of what the force of gravity looks like as a function of our vertical displacement. Okay, which is kind of a silly thing to do, but I want to make a point, all right? So check it out. Let's do this. I'm going to go 2 pages here. All right, so let's give ourselves some axes. So the idea is we want to make a graph that shows us, as a function of our vertical position measured in meters, what is our force of gravity, okay? Well, our force of gravity is constant, right? Our force of gravity is just negative mg, right? So if I call this 0, and I call this negative mg, then regardless of what my position is, so suppose I have some initial position and some final position, right? Regardless, my force of gravity is always just negative mg, right? Okay? All right, so let's take a look at this. So what we know is this. Let me do this in red. All right, so the work done by gravity should be equal to the force of gravity, which is negative mg, times our vertical displacement, which is y final minus y initial, right? So that's negative mg times, y final minus y initial. It's this area, right? Okay. So here, and we'll learn, and always, it turns out to be true that the work done by a force is equal to the area under the force as a function of position curve. Okay, so let me talk about 2 things here. So first of all, position, I mean generically, right? In the case of gravity, our position is actually y, right? Okay, and when I say the area under, one of the things we talk about in calculus is when you find the area under a curve, what you're really doing is finding the area between the curve and the horizontal axis, okay? And so in this case, the work done by gravity is going to be negative, right? Because I've got a negative force and a positive displacement, right? Okay? So, so this is negative mg delta y, work done by gravity. Okay? All right, so that one wasn't too bad because the force was constant, right? The force was constant, which is why this graph looked like that, right? The force was constant, okay? So, what happens if we've got a force that is not constant, okay? Oops. All right, so let's take a look at a spring, okay? So I'm going to use Fe to represent the force of the spring, E for elastic, right? And unfortunately, stupid formatting moved this. So the idea is our elastic force is negative kx. All right. So what I'm going to do is, I guess, so I'm getting ahead of myself. All right. So this time, and this is super, super important. Super important. We can't use work equals force times displacement because the force isn't constant. All right? And so because the force isn't constant, we need to find a way to calculate the work and accounting for the fact that the force is changing. All right? So I'm going to make the same graph I made before. I'm going to make a graph of force as a function of position. All right? So let's do this. So here's my horizontal position. I want to make a graph for the elastic force exerted by that spring. All right, and I remember that that's simply equal to negative kx, right? So no matter what k is, this is basically, so quick side note. So in general, if y equals mx plus b, that's the equation for a line, right? Here's what we've got. Elastic force equals negative kx plus 0, right? So we've got a y-intercept of 0 and a slope of negative k, okay? So in English, we're going to have a straight line with a slope of negative k. So that graph is then going to look like this, right? Okay? So let's calculate the area under the curve and see what happens, okay? So let's assume, for simplicity, let's assume that our initial position is 0, okay? And then we're going to some final position, okay? So based on what we learned a minute ago is this, that the work done by our elastic thing, by our spring, it should be the area under the graph, under the f of x graph, okay? Sorry, I paused there for a minute because I was thinking to make sure my signs would work out the way I wanted to, and they will. All right? So, well, let's see. So what I want then is so one of the things you hopefully learned in algebra is that the area of a triangle equals 1/2 the base times the height, right? So for us, here's my base. Right? Times our height. Okay? And this, well, let's see, this is just going to be negative k times x final, right? So our height is negative k times x final, right? Okay? And so that'll give us this area, right? Okay, well, let's see what that gives us. So we decided that our x initial was going to be 0 for simplicity, right? So this guy goes away, right? And so now I'm looking at negative 1/2 k times x final squared. Huh, that's the same as, that's almost the exact same as the elastic potential energy equation, right? Okay. Oh, but remember this. Remember, we learned that the work done by a conservative force is equal to the opposite of the change in its potential energy. So the work done by the spring is equal to the opposite of the change in elastic potential energy. Oops, sorry. I wanted to use an E here, right? Which makes sense here, right? Because my elastic potential energy initially here would be 1/2 k times 0 squared. My EPE final is 1/2 k times x final squared. So when I do final minus initial, I get this. And the work done by that should be negative that. Okay? So once again, this reaffirms our idea that the work done can be calculated by finding the area under the f of x graph. So once again, the work done by a force is area under the f of x graph. Okay? All right. Now, area under a curve. Well, in math class, we refer to that as an integral, right? A definite integral specifically, right? Because you're finding the area between two fixed points, right? Between your initial and your final point. So this area is a definite integral, okay? All right, so what all of this kind of shows us, I guess it doesn't prove it rigidly, but it begins to suggest this idea that the work done by a force can be calculated by taking the integral of f with respect to x, right? Because remember, this is fancy speak for the area under the f of x graph, right? Because that's what an integral represents. It represents the area under the graph, all right? So, for example, in the case of the spring, let's check and make sure this works. Okay, so the work done, so the work done by an elastic force is equal to the integral from our initial position to our final position of the force by that elastic force, right, the force of the spring basically, with respect to x. So this is the integral from initial position to final position. Remember, this is just negative kx. Right? Okay, so the integral of negative kx, well, our integral is, so what do we have to take the derivative of to get this? So it must be x squared, but we got to get rid of the 2 when you bring it down, right? So I think we're going to get negative 1/2 kx squared. So take a second and convince yourself that if you take the derivative of that, you get this. All right, bring down the 2. 2 times 1/2 is negative, or is 1, and the negative sign. So you do get negative kx, and then we need to evaluate it between x initial and x final. All right, and so this is, oops, this is an f. So plug in your final, so you get negative 1/2 k times x final squared minus negative 1/2 k times x initial squared, which is the same as negative 1/2 k x final squared minus 1/2 k x initial squared, which is negative change in elastic potential energy, which we already knew. Okay? So, this becomes useful, this idea becomes useful if you've got more complicated forces, right? If your force is constant, then great, you just do work equals force times displacement. In the case of a spring, we already knew how to do this, but suppose I give you some sort of potential force that's, I don't know, like, whatever, maybe 4x cubed minus 2 or something, and I want to figure out how much work is done. Well, you just do that by integrating, okay? All right, so, there you go. All right, so this next point here kind of shows us the same thing. So this idea is that it works for any variable, any non-constant force. All right, so here's an example that doesn't have cubes like that last one did, okay? So here we go. So it says we've got a net force acting on an object, okay? And our net force is given by 12 plus 1.4x newtons in the I direction, okay? It's applied to an object that is initially at rest. How much work is done by the force as the object moves from an initial position of 0.50 meters to a final position of 2.50 meters. All right, and we're trying to find out how much work is done by that net force, okay? So we're looking for net work. Oops, that says net if you can't read it. All right, well, so here we go. So the work done by the net force should be equal to the integral from our initial position to our final position of our net force with respect to x dx. So that's the integral from, let's see, our initial position is 0.5, our final position is 2.5, our net force is 12 plus 1.4x dx. So now we integrate that. So the integral of 12 is 12x plus the integral of 1.4x. Well, we need squared, right? So x squared, bring down the 2. What times 2 is 1.4? Oh, 0.7. And then you want to evaluate it at 0.5 and 2.5. So you get 12 times 2.5 plus 0.7 times 2.5 squared minus, running out of room, 12 times 0.5 plus 0.7 times 0.5 squared. And just plug your numbers into your calculator. You end up getting 34.375 for the top part, minus 6.175 for the bottom part, and it gives you 28.2 joules. All right, so there you go. So that is how you can calculate the work done by any force, okay, as long as you know what the force is as a function of position. All right, now, frequently what will happen is instead of being given an equation for the force as a function of x, you'll be given a graph of the force as a function of x, okay? And that's exactly what we've got here. Here's our force as a function of our position, okay? And so we're going to find the work done by the force as the cart moves from our initial position of 0 to whatever, all right? So basically all you're going to do is you're going to break this thing up into chunks, okay? And you're going to find each of the areas, okay? So for this chunk here, let's see, so half base times height. So half of our base would be 2 times 12, so that looks like 24 joules. Notice the units do work out because we're doing newtons times meters, which is what a joule is, right? Okay, and then I want to do this chunk here. So I think that's the same thing, right? Except it's negative 24 because it's below the x-axis. All right, and then this chunk here, probably should have paused this so you could draw your graph. So now it's just a rectangle. So this side of here is 3 times 12, so that looks like negative 36 joules. All right, and then this chunk here is, let's see, it's got a base of 2, so half of that is 1, so that's just going to be negative 12. All right, I got to repeat my colors now, so I'm going to go back to yellow. So this chunk here is positive 12. And then this last chunk, go back to blue. I said we'll go back to blue. This chunk here is 3 times 12, which is 36. Okay, so the work done in the first 4 meters is just 24 joules. By the time you get to 8, you're going to have 24 minus 24, so you actually get 0 joules. By 11, you're going to be at negative 36. All I'm doing is just adding up, right? For the next chunk, you're going to get, what, negative 48 joules. For the last, let's see. So now I got to add on another 12, so I'm going to go back up to negative 36 joules. Plus 36 gets you back to 0 again. Okay? So I literally just added up each of these areas as we went along. Okay? So this is a super common thing where you'll be given a force as a function of position graph, and you got to find your work done. Okay? All right. All right, now, I'm going to say, what about going the other way? And you'll see what that means in a minute. All right? So now, notice that if the force is constant, so we're moving on to something new-ish here, okay? So if the force is constant, we've got this equation, right? Algebraically rearranging that gives us this, that the force exerted by a force is equal to the work done by that force divided by the displacement, right? If the force is constant, right? So in the case of gravity, the force exerted by gravity should equal the work done by gravity divided by the vertical displacement. That's the same as, remember, work done by a conservative force is equal to the opposite in the change in potential energy divided by delta y, right? So mathematically, this first thing is easy. So check it out. This is this. Fg is equal to negative ug divided by delta y, all right? Well, let's see. Ug, that's gravitational potential energy. So this is negative mg delta y over delta y. The delta y's cancel, you get negative mg, which is our force of gravity. Hooray, it works. All right? So, but we need to think of this in more general terms. All right? So, let's do this. So, suppose I calculate, I'm going to graph the work done by gravity as a function of y. Okay? But I'm going to do it in a sort of a roundabout way. Let's do this. I'm going to make two graphs simultaneously. So let's take a look at the gravitational potential energy, i.e. Ug, right, as a function of our vertical position. So if your vertical position is 0, then your gravitational potential energy is 0. As your vertical position increases, right, because it's just GPE equals mgy, right? So as y goes up, so does your GPE, so you just get a nice straight line, right? Okay. So then, suppose I wanted to graph the work done by gravity. Well, remember, the work done by gravity is just equal to the opposite in the change in ug, right? So I can call this delta y. I guess I could call this delta y if I had wanted to. So the work done by gravity is just the opposite of the change in gravitational potential energy. So that's just going to look like this. Okay. And so what is my point? My point is that if we take the slope of this, all right, sorry, I had to collect my thoughts there. Okay, so my point is, if you take the slope of this, well, look. So this green graph over here, we already had this equation, but I erased it because I'm dumb. Our GPE is mg delta y, right? So the slope of this line is our force of gravity, right? Which means that the slope of this line must be negative mg, which is our force of gravity, right? Oh, so that means that if I take the derivative of my work graph, it gives me the force. Okay? There's a lot of work to get there. So here's what we just learned. We learned that the derivative of the work done by gravity with respect to our change in position is the force of gravity. Okay? That's the same as the opposite of the derivative of the potential energy graph with respect to position. Okay? The delta y there is a little redundant because the d kind of means change in. So I guess we can just put dy here and put dy here. Okay? But so this is the big thing. Okay? The derivative of the work done by a force with respect to position is equal to the force. All right? Let me write that in general terms because this is important. The derivative of the work done by a force with respect to position is equal to the force. Okay? All right. So let's check that in the case of a non-constant force. Okay? Because here we've got a constant slope, constant force, right? Now, what about if the force is not constant? So in the case of a spring, our force changes, right? So if I wanted to make a graph of, what was I taking the derivative of before? Work with respect to x, right? So the work done by a spring is equal to the opposite of the elastic potential energy, which is negative 1/2 kx squared, right? So I'm going to kind of do the same thing, right? So here's elastic potential energy as a function of position. So that's 1/2 kx squared, right? So that's going to give us just a parabola, right? So that means the work done by our elastic thing is that, but flipped over, right? Because they're negatives of each other. Okay, so that's negative 1/2 kx squared, right? All right, and so suppose I want to find the slope. Suppose I want to find the force, rather. Okay, well, our elastic force should be the derivative of the work done by the elastic force with respect to position. So that's the derivative with respect to position of this. And if you take the derivative, 2 times negative 1/2 is negative 1, and it gives you negative kx. So there it is. There's our elastic force equation, right? All right. So here's everything summarized. I stumbled on this a little bit earlier, and I forgot that I put a slide in, so yay me. So in general, for just any old force, you can always calculate the force by taking the derivative of the work with respect to position. Okay. All right. All right. And so again, this works for any variable force. It doesn't just work for gravity and springs. So let's do one last example, and then I think I'm done with you here. All right, so this works for any variable force. All right, so if I tell you that the work done by some force is this, so the work done by our force is negative 4x squared minus 5x plus 7, with x in meters and work in joules, then you can find the force being applied at any given time. So the force is just the derivative of the work with respect to position, which is then this, the derivative with respect to x of negative 4x squared minus 5x plus 7. So the derivative of that is, let's see, you're going to get what? Negative 8x minus 5, right? So now I can figure out how much force is being exerted dependent on my position. All right? Probably worth noting, remember, derivative is a slope. So I'm going to, on the fly here, I didn't put this example in my notes. What if I give you this? What if I gave you a graph for some random function? So here's a function. Here's some random force. Here's how much work is done by that force as a function of the position. Okay? And maybe the graph looks like, I don't know, maybe it's here. You know, whatever. Maybe it zeroes out, or maybe it goes down again, right? And I ask you, you know, how much force is exerted at x equals 5? Well, that would just represent the derivative here, which is just your slope, right? Okay, so if you remember that the derivative of a graph is the same as the slope, then what I would just be doing is I'd be finding the slope. Find the slope of this line, and that would tell you how much force is being exerted when the position is 5 meters. Okay? Because slope is derivative in this case. Okay? All right, now, the final thing that I need to call to your attention here that I've sort of, I don't know if I'd say glossed over it, and because it's not super important yet, but it will become important, is this, that right now, our horizontal axis on all of these graphs is position. Okay, that's why these are all dx. Okay, that is huge. All right, because later on, so here, I guess maybe getting ahead of ourselves. So here's what we've learned so far, or what we learned today is this: that force is the integral of work with respect to x. Okay, so just note future things to come. All right. Eventually, we're going to figure out that force is the no, I'm sorry. Hold on. Rewind. Pretend I didn't just say that. Sorry, I knew something funny was funny there. All right, rewind. So what we just learned is this. Oh my goodness. The work done by a force is equal to the integral of the force with respect to x, right? Okay, so back on track. So note, for future reference, eventually we're going to learn this. Change in momentum is also the integral of force, but not with respect to x, with respect to time. Okay, so please be careful when we're dealing with work and your horizontal axis has got to be x, okay? And then eventually we'll get to this where our horizontal axis is time, okay? Which, to be honest, I think this one is easier. But anyway, that is that. I apologize about the little blip there. I'm not re-recording because I don't want to go back and re-record a 30-minute video for a 1-second error. Have a good day.